Dear students, in last class we studied complex numbers, representation of complex numbers on complex plane, and then we studied what is the magnitude of complex number, how to calculate it, what is the argument of a complex number, and so on. Knowing I is equal to root of minus 1, I square is minus 1. In polar form, I is written as one at an angle of 90 degree. I square is 1 at an angle of 180 degree. I cube is 1 at an angle of 270 degree. I raised to 4 is 1 at an angle of 360 degree, or that is equal to 1 at an angle of 0 degree. Now we will see how the complex numbers are added, subtracted, multiplied and divided. Operations on complex numbers. First we will study addition of complex numbers. Say we have two complex numbers. One is x1 plus iy1 and another one is x2 plus iy2. If we have to add these two, we have to add real part and real part and imaginary part and imaginary part. So x1 plus iy1 plus x2 plus iy2 is equal to x1 plus x2 plus I into the bracket y1 plus y2. Next, subtraction of complex numbers. if I have two complex numbers a1 plus ib1 and a2 plus ib2, to subtract a2 plus ib2 from a1 plus ib1, we have to subtract a2 from a1 and b2 from b1. That is a1 plus ib1 minus a2 plus ib2 is equal to a1 minus a2 plus I b1 minus b2. Multiplication of complex numbers. So we have two complex numbers x1 plus iy1 and x2 plus iy2. If we have to find the product of these two, that is x1 iy1 into x2 plus iy2, then you multiply the two brackets here as you multiply two binomials x1 into x2 plus x1 into iy2 plus iy1 into x2 plus iy1 into iy2. But multiplication of complex numbers in polar form is easier. That is, if x1 plus iy1 is equal to r1 of theta 1 and x2 plus iy2 is equal to r2 at an angle of theta 2, then x1 plus iy1 into x2 plus iy2 equal to r1 at an angle of theta 1 into r2 at an angle of theta 2. Multiply magnitude and magnitude, and then add the angles. Now this is the product. Similarly, division of a complex number by another complex number is easier in polar form only. So you have two complex numbers, a1 plus ib1 and a2 plus ib2. Let a1 plus ib1 is equal to r1 at an angle of theta 1 and a2 plus ib2 is equal to r2 at an angle of theta 2. Now a1 plus ib1 by a2 plus ib2 is equal to r1 at an angle of theta 1 divided by r2 at an angle of theta 2. Divide magnitude by magnitude. R1 by R2. Subtract theta 2 from theta 1. Now this is the result of the division of a1 plus ib1 by a2 plus ib2. Remember, I equal to 1 at an angle of 90 degree is called "90-degree operator". Reason for this is if you have a complex number if we have a complex number z equal to 1 plus say I0, z into I will become 1 plus I0 into I, that is 1 I only. On complex plane, real axis, imaginary axis, So we have complex number z equal to 1 here. Now if I multiply z by I, it becomes zi, that is equal to 1i. 1i means 1 into 1 at an angle of 90 degree. So it will be now 1 at an angle of 90 degree. 1 at an angle of 90 degree means I have to show 1 at an angle of 90 degree on imaginary axis, that is here. So this is 1 now, and 1 here is now rotated by 90 degree. That is why I is called as 90 degree operator. If we multiply any complex number by I, that complex number will be rotated by 90 degree in anti-clockwise direction. So this number here is nothing but now z into I. Now you can imagine where will be z into I square and where will be z into I cube. Complex conjugate of a complex number. If z is defined by a plus bi, then complex conjugate of z is written as z star and is computed as a minus bi. If we have another complex number, say x equal to p minus qi, then x conjugate is p plus qi. So what is the meaning of complex conjugate of a complex number? The complex conjugate of a complex number is nothing but a complex number with the sign of imaginary part changed. Here we had plus, in complex conjugate it has become minus, and in complex number x, imaginary part is negative, and in the complex conjugate of x, the imaginary part is positive. You all have studied signals and systems in your previous semester, and there you have studied discrete time Fourier transform. Discrete time Fourier transform is used for the frequency analysis of discrete time signals. The discrete time signals are those signals which are defined at discrete times, but their magnitudes are continuous. To find what is the frequency content of such signals, we make use of discrete time Fourier transform. But this discrete time Fourier transform has got a drawback. That is, when a discrete time signal is transformed into frequency domain, it will be a continuous function of omega, and so it cannot be processed by digital system. The discrete Fourier transform DFT has been developed to convert a continuous function of omega to a discrete function omega, so that frequency analysis of discrete time signal can be performed on a digital system. So why DFT is defined? DFT is defined to convert the frequency domain representation of discrete time signal into discrete one. So we'll write explanation for it first. The DTFT is used for representing a discrete time signal into frequency domain. The drawback of DTFT is that the frequency domain representation of a discrete time signal obtained using DTFT will be a continuous function of omega, and so it cannot be processed by a digital system. The DFT has been developed to convert a continuous function of omega to a discrete function of omega. So that frequency analysis of discrete time signal can be performed on a digital system. Now a question must arise in your minds. How is a continuous function of omega is converted into discrete function of omega by DFT? Basically, it is done by sampling the DTFT itself. How it is done? It is done by sampling the DTFT itself. It means that DFT, that is discrete Fourier transform, is sampled version of discrete time Fourier transform. And how the sampling is done? the sampling is done uniformly. The sampling is done uniformly. So what question you must have here? How? The discrete Fourier transform of a time signal is obtained by sampling discrete Fourier transform at n uniform frequency intervals. And the number of samples that is value of n should be sufficient to avoid aliasing of frequency spectrum. So in nutshell, we have to understand the process here as the discrete time signal is transformed into frequency domain signal by using DTFT. So in frequency domain, the signal is represented as x of e raised to j omega. X of e raised to j omega. And this x of e raised to j omega is sampled to get dt to get this x of e raised to j omega is sampled to get x of k, where x of k is the discrete Fourier transform DFT. So this is DFT here and this is DTFT here. Where k varies from zero to n minus 1. X of k is complex number. X of k is a complex number. That means for k equal to 0, x of 0 will be a complex number. For k equal to 1, x of 1 will be a complex number, and so on. The plot of magnitude of x of k versus k is called magnitude spectrum. The plot of phase angle of x of k versus k is called phase spectrum. Generally, these two plots are called frequency spectrum. Are called frequency spectrum.